Armand also made sure that he had pizza through his employer today, so thank you all for giving an applause for that. Thank you for Communitech for the Data Hub, and now we will have the second talk of the evening, and Armand will be talking about adversarial AI.
Thank you. First of all, what a turnout. Thank you, Mary. I wasn't expecting this, but I think the weather is helping. So welcome, everybody. Really happy to see all the new faces and the old faces that I met with a few of them last November, I would say. So for those of you who know me, I have this habit of putting this first slide at the beginning of all my slides. I love this guy. He's a visionary philosopher, so I encourage you guys to go and read more about Walt Emerson. He has a lot of very nice essays to read. He's a poet, a philosopher, pretty intelligent guy. So this thing that he said, I don't know when exactly, is I think the sheer reason why everybody's here. That's why I usually put that at the beginning of all my slides. So with that being said, today I'm going to talk a little bit about adversarial AI. And the subtitle for this is There's Learning in Competition. So before jumping onto the topic of the day, I just wanted to also introduce myself. My name is Armand, as Barry mentioned. I work with Space, which is Deloitte's innovation lab located in Curelet-Balan downtown. And I also have one of my friends here today. Who I am, and very recently I have started with a few of my colleagues that are also here to work on a project, and this is a bit of a knowledge that we kind of gained in order to start that project, and I wanted to share it with everybody here. So what I hope that you guys would take out of here with you is what is this guy talking about when he says adversarial AI? Also a little bit of introduction to some of the most important names within this domain of AI. I also mentioned competition in my subtitle, so there's a game sense of what I'm going to talk about as well. So there's some gaming involved, so to speak, and that connects to why we need deep neural networks to do this type of AI, adversarial AI. And then hopefully I could wrap up with some examples depending on how much time we have. But before doing that, I also wanted to point out a few of my colleagues who are helping me with this project. I encourage you guys to talk to them, ask them questions. I will not probably be able to answer all of your questions if you have any, but we have Zahra here and you. I don't see Jerry. Oh, there he is. So hands, wave to everybody, and then they would know where you're sitting. And this is a very cool picture of us doing design labs today. So I just wanted to know the faces and then go and ask them questions, and hopefully they will help answer some of the questions as well. With that being said, let's jump into the actual topic of the day, adversarial AI. But what am I talking about? What is adversarial AI? In order to be able to define that, we need to know what an adversary is. So by definition, adversary is one's opponent in a contest, conflict, or dispute. And using that definition, basically what adversarial AI represents conceptually is when you have one AI system that is trying to fool another AI system. So that is why those two AI systems are adversaries to one another. And specifically with AI systems that are machine learning based, then you have machine learning models that are trying to build outputs that are slightly different than what is expected them to output, but they're so close to the expectation that it's not really easy to distinguish between those two. And that is how they try to fool the other AI system. So that's basically a wrap-up of what adversarial AI is. This is like an abstract of what I was going to talk about. So basically the rest of this evening is going to be going more in depth into all of these different components of adversarial AI. Very famous textbook examples, whenever you just go and Google adversarial AI or adversarial machine learning or training and so on and so forth, there are these types of pictures when you have an image that belongs to a specific class or category or label or whatever other term you want to use when you're using a machine learning-based classifier. And the classifier is, for example, going to give you Panda or a pig. And then through adding some very small level of noise or perturbation, you could fool the classifier into classifying with very high confidence the picture that it won't really seem different to our human eyes, but they would, with high confidence, say, no, it's no longer a panda, it's a gibbon, or it's no longer a pig, it's an airliner. That's a classic textbook example of what adversarial machine learning or training would basically represent on the web. But that's not it. And we will look into that. But this is how far we have come so far in the past almost 5-ish years. So end of 2013 all the way to 2018. This basically this picture shows how far this adversarial training of machine learning have improved. And I have also gathered 8 examples of this website, thispersondoesnotexist.com, and I encourage you to play with it whenever you have some free time or over lunch. These 8 examples are sampled from 11 attempts that I made to gather pictures that are very similar to what we expect they should be. So 8 out of 11 are like this. 3 of them were not really, it was distinguishable, so to speak. So just put them aside, but that's the rate that you could expect these days out of this system. And most of the similar systems that are using adversarial training are kind of similar to this. Very recent example that I didn't add to this is if you go to YouTube or basically Google it, you would see these videos of making Mona Lisa or any other picture talk to you with whatever text that you could give to it. So it's basically replicating the way that faces are moving to talk about any specific concept from a static image. So that's another very recent shift in the academic domain when it comes to adversarial AI. And it's a very nice tool to toy for me at least. It's something that you could play with and then get a sense of how we can get fooled by these types of systems. But as I said, images and building these types of images or videos are not the only use cases of it. There is research in autonomous vehicles for when a network, so to speak, or any classifier, could see a picture, for example, of a stop sign, but then you could, or somebody could carefully construct some sort of noise and then put it on top of the stop sign, and then the camera of your autonomous vehicle would transmit that back to the backend classifier, and the classifier would think that that's a spoon, and God forbid would pass the intersection and hit somebody. So that's another area of research that people are focusing on. Again, that's vision, I know, but it's different than generating faces and stuff like that. There's also this other area that is focused on the vulnerability of confidential information. So for example, if you have a network's intrusion detection system that acts as a gatekeeper, and then this IDS system is going to let malicious input that is disguised as normal input pass and get through your system. This is happening by basically changing some of the non-functional signature or features of the input, basically vector. That's another area of research that is very active these days. So as of maybe 2.5 years ago, very active, but it has been active for the past 5 or 6 years as well. One thing that I forgot to mention, if at any point in time you guys have a question, raise your hand, call. It's better to stop where we're talking about something, as opposed to going all the way to the end and not having time to talk. So it's better if we have some sort of a discourse. You should know all of this.
What is non-functional mean?
Great question. So whenever, if you're talking about network traffic, there are different features that represent a network traffic. So for example, inside the header of a packet, in a TCP packet, for example, there are some features, some attributes of this packet that if you change them, it changes the nature of that packet. So any IDS would directly and right away would know that, hey, this is malicious. So when people are doing research in this area, they try to keep the functional features and not touch them, and then go and try to attack the non-functional ones so that the ID assistant wouldn't recognize that type of change or noise. So thanks for that. Okay. Now let's take another deeper look at what adversarial training is all about, and why, when we say generative adversarial networks or generative adversarial AI, why do we call that generative? So this guy, the poster boy of generative adversarial networks, Ian Goodfellow, who has worked with Google Brain, OpenAI, Apple. I think he was at some point at Facebook as well. I can't remember for sure. But he has worked with the likes of Jeff Hinton and Yashua Bengio in Montreal. So everybody knows him as the inventor of generative adversarial networks. In the main paper, the NIPS paper that they published in 2014, where everybody thinks that's basically the beginning of generative adversarial networks, these guys mentioned that competition drives both teams, so both agents or both individuals, to improve their methods until the counterfeit, or one of these agents, or one of these teams, is indistinguishable from the genuine one. So basically you have two different entities that are trying to compete against one another, and one is trying to beat the other one by trying to replicate basically its behavior. Now that could be anywhere. That could be in the images domain, that could be in the video domain, in intrusion detection, and so on and so forth. So once again, Ian Goodfellow, poster boy of generative adversarial networks, worked with the best minds, at least in North America. But then there's also this idea, or at least the coining of the term adversarial networks, or adversarial training at least, is much older than that. Arthur Samuel in 1958 said that algorithms could learn to play checkers via adversarial self-play, which basically means if you have an algorithm that is trying to learn to play checkers or any other game, it could play against itself and try to improve its behavior over time. And Arthur Samuel has worked with Bell Laboratories, University of Illinois at Urbana-Champaign, IBM, Stanford. So he was also very famous back in the old days, where it was right before the winter of AI, so to speak.
So how is it different from reinforcement learning?
I will get to that. That's one of the sections that I'm going to talk about is actually the difference. It will show you how the difference is. I'm not going to tackle reinforcement learning, but yes, there is a difference. Okay, so there's a lot of discussion these days around the fact that Ian Goodfellow is not really the actual inventor of this, and so on and so forth, and there's not enough innovation in what he has done, but I think he was innovative enough, even if he got this idea from Arthur Samuel and his colleagues from half a century ago. What they have done, I think, is amazing, but I just wanted to let you also know that this also exists. And so we also mentioned about deep learning. For anybody who is not familiar what deep learning is representing, it's very simple. It's basically you have a few different neurons represented by these circles, and they're also connected to one another through different layers. The old artificial neural networks. And now we have a lot of compute power, so we could add layer after layer after layer, so the number of hidden layers is going to be much more, and the architectures are going to be more complicated, and different types of neurons, and so on. But basically, that is what a neural network looks like in the easiest shape and form. And once you have such a neural network, more complicated than that, obviously, the generative aspect of these networks come into play. So basically what you would have is you would input some random variable that is drawn from a simple or non-simple distribution, and then that would represent a vector of numbers. So basically a 1 times, let's say 1,000 dimension, and then that would go into some network that is more complicated than this, And then the outcome of that is going to be the fact that the generative network is going to transform or translate this vector into something that is more complex. So you start with something that is simply drawn from a random variable, you pass it into a network, the outcome is going to be something more complex. And this output is then going to be what you're looking at, and then you change the shape of that, and it could be something like a picture of a dog or an elephant or anything like that. So that is when we say generative, that is what we're talking about. The generation or the transformation of this very simple vector that you're sampling from anywhere, some data space, and then translating it into something that doesn't exist. And that's why it's generating stuff. But why do we want to do that? This picture shows the exact reason behind that. So there are a lot of elements on this picture, so I'm going to go and take a look at each one of them one by one. So here you have this black bold line that is representing the boundary of the classifier that you're trying to train. So for example, in the sense of, and this is just a binary classification problem, so let's assume you have Panda versus gibbon-ish, and then you have two different types of elements in this data space. You have the circles, the reddish circles, and then the blue crosses, your two different classes. And the classifier that you have trained, whether it's a very simple classifier all the way to most complicated deep neural network-based classifier, is able to distinguish these networks using this boundary. So anything that is on this side of the line is going to be categorized or classified as the dots, and anything is on the other side or left and top of that line is going to be classified as a cross. However, in real life, we can usually never get 100% accuracy. So the task decision boundary is actually this dashed line that you can see here, which means there are some cases that your classifier is going to make some mistakes. And that is why you could never get 100% accuracy. Now, the light red and light blue examples that you can see here are things that you're training your classifier with. When you get to the dark ones, so this red example and this blue example here, these are the things that you're going to test with. So this is your test set. And that is why there are some cases where these examples that belong to this test set are going to be misclassified or by this line that is representing your classifier. The idea of adversarial examples lies right there. What we are trying to find when call them adversarial examples are things that lie in between these two lines. So anything that sits here, in between this space and here, are things that are adversarial, technically. And the generative network is trying to take something from this line of your classifier and push it slightly to the other side, but only enough that it doesn't pass the actual task decision boundary. So that when you see a picture of Panda here, with some level of noise, it would go past the line that is saying, is it a panda or is it a gibbon? But to the human eye, it still looks like a panda. That's basically the gist of what adversarial examples are. The outcome of your network or any other system that is pushing this, this actually actually panda, all the way to the other side of your model decision boundary, so that the model decision boundary makes a misclassification, but it shouldn't go past the actual task decision boundary, so that we still think it is a panda. And that's it. Now, let's get back to the fact that I mentioned that you have two different entities, two different players, agents, or teams. Those two are your generator and your discriminator. These are the two, so to speak, agents that are working together and still competing against one another in order to build these types of examples. What's happening here is that you have two components that are kind of hand in hand working together. First of all, you have a discriminator, which is like a regular classifier. All it does is that you give it, let's say, some images or some packets or whatever else, and it will try to come up with this decision boundary. So it's technically a classifier, but you don't start training it with a lot of training data. You start from basically making random guesses at the beginning and trying to improve it over time. So what's happening here is that you get some real samples, and your discriminator is going to start making some decisions based on those. And then the discriminator is going to ask some sort of teacher that knows about everything, like in Oracle, in active learning, if anybody is familiar with that concept. And then through asking these questions or queries, the discriminator is going to improve itself over time from just randomly guessing all the way to getting, let's say, 98% accuracy. So this is where the fine-tuning of the training of the decision of the discriminator happens. So it makes some guesses, then goes to the teacher and says, hey, did I make a mistake or was that correct? And then the teacher would give some feedbacks, and the discriminator is going to improve over time by learning from the mistakes that it made. The second component is the generator that you saw in a couple of slides ago. So here you have a latent space that is representing, again, your images or your packets and so on and so forth. And these are representing this and this, or this. So you add a level of noise to that and pass it into your generator network. And this is going to generate some fake samples for you. Now, the second phase of this co-training that is happening is the discriminator is also going to make some decisions on these fake samples. And because the discriminator is starting by randomly guessing, for some of these fake samples, the discriminator is going to say, well, this is probably a panda, and this other one is probably a gibbon, because I'm just randomly tossing a coin. But over time, your D function, your discriminator, is improving, right? So in order for your G to get better and better over time in making these fake samples, it needs to go and try to fool your discriminator. And because your discriminator is improving, your G is also supposed to improve over time. Because there's another line of feedback that is coming from this decision back into G. So over time, I start with some, let's say, image that doesn't really look good. I give it to my D, so let's say 100 of these, and my D function is going to say yes, no, yes, yes, no, no. But then after, let's say, 100 iterations of training my D, it would get a sense of what I'm trying to use to fool it. So if I want to fool my D, I need to generate better samples, better fake samples. So through that feedback loop, as G, as that agent, I have to improve myself as well. And the improvement is happening through, in this specific case, deep neural networks. I need to get better and better over time. So we will see how that happens in a few minutes. But this is the whole idea of competing against one another while collaborating in order to beat basically this teacher at the end of the game. And some important components here is that the real data you have to have, things that you already know, this is your training set in the regular machine learning, and you have this latent space defined in a way that you could represent it, you could pass it into your generator, and you also have some noise that you are sampling from some noise space.
In your Panda example, who is the teacher? How you can define it?
The teacher could very easily be the person, you and me, who is sitting and saying, this is a panda, this is not a panda. So one human being, so to speak. So, or a very good classifier.
And the generator and discriminator both are neural networks, yeah?
Yes. I would say most of the cases, yes. They don't have to be. But in all of the cases that are working, yes, they are neural networks. And they don't have to be the same. They don't have to have the same architecture or the same types of neurons. Sorry. Yeah.
So I don't think I understand what latent space is. Maybe equivalently, I don't think I understand what input the generator takes.
Sure. Just to give you a very easy example of that, we looked at the panda image, right? no machine learning model can take that into itself as an input, right? So you have to translate that into some numeric value, so to speak, right? So when you have an RGB picture, you have to translate that into a vector of numbers. That is how you define your latent space. Now, you could include just the RNG channels. You could also add alpha. You could start adding something to it. You could reduce something from it, and then define your latent space, so to speak, in a way that works for the case that you're trying to solve. But all in all, it's a way of vectorizing your input from what exists in the real world to something that is a numeric representation that any machine learning model could digest.
So is it like just the bitmap of the picture? Because that seems to me like what the real samples are, right? You give me a
The real
picture,
samplers are
I turn that to a bunch of pixels, I feed that to the discriminator.
Could be that, yep.
But then the latent space is the same thing or it's a different thing?
Depends on the use case. To be honest, based on what I have seen so far, and I cannot say for sure that they have to be different, but based on what I have seen in a few different use cases, they could be the same thing, unless you need your generator to try and generate different stuff. So for example, the latent space of generating videos off of static images is different than what you are trying to classify with, right? Because your D is not really classifying static, your D is not classifying videos. Your D is classifying frames. So what it takes is a static image. But your G could be taking in videos in whatever type of form. But most of the examples that I have seen so far, the latent space is basically how you're going to translate this into a numerical value or vector that D or G could digest. And again, I might be wrong. I can't really say for sure, but this is my understanding. You want to go next?
I have the exact same question.
Cool.
Yeah. Okay. I have a question. I know we use against a network. We could create fake images, right? To increase the data. Could it be? Is it could be used in the non-image data?
Yes.
If so, how could we verify it? Because by images, we could create a fake image by eyes. Okay, see this panda. This not looks like panda.
Mm-hmm.
But for normal like categories data or numerical data, how to verify?
So your question is basically this, right? How can we make sure that this is yes or no?
Well, I would say, well, by this discriminator, we create the fake data for numerical, right? Then we got many data. Then okay, well, how can I see this data is good or not?
So that's actually one of the problems that we are also trying to solve. In order to get your real samples into, let's say, that latent space, you have to pre-process your, in this case, images, right? Now, if you don't have images, you have other stuff, right? So for example, let's say you want to build a drug that is fake. Then you have to pre-process your whatever you have, your categories, your numbers, whatever, into something that is digestible by this. If you want to have somebody like George and myself to sit down and say, I'm a subject matter expert and I'm going to make that decision, you also have to post-process what you have generated in order to be tangible for somebody like you and me to sit down and say, yeah, this looks like a drug, but I could see that it is fake because of this. So that is post-processing after. So there could be an added layer here where you could say, I'm translating these into this, but I'm also, the outcome of this, I'm going to translate this back to these real-looking samples so that I could make a decision based on that.
So it means anyway, we need some metrics to see, oh, this is the correct data. This is very similar to the correct data.
Exactly, yeah.
Okay.
But to you and me, to him and I, in the image case,
Yeah,
we can't really define
see it, yeah.
something if you are sitting there and clicking on yes or no, right? Because our visual cortex system is making that decision for us.
But could we just treating the real data as a model? For example, well, then we got some metrics, accuracy, precision. Then we treat the fake data as another model to compare different.
We could, yeah.
Yeah, we use it as metrics, so it makes sense, right?
Yeah, makes sense to me.
Yeah, sense.
Other hands. George, go ahead.
Do you need also to fine-tune the noise? What if you don't put enough noise and the data you get is not fake?
So the fine-tuning of the noise distribution sampling is happening through the fine-tuning of G. What G is doing is just a function, right? So the feedback that it's getting from D and the teacher is making it move towards the way that is the type of noise that it wants to generate, as opposed to just randomly sampling from, let's say, a normal or a uniform distribution.
Probably it's a very basic question, but I'm a bit confused about that suggestion. Like, if the system, the network, can be fooled by the fake image, and as a human being, we are not fooled. Like, we can recognize they are Panda, right? Even if you add the noise, then how good is the network?
So that's the case. That's exactly the case. This is not a Panda. So if you pass this into, where is this guy? Into this classifier, you won't, when you have a self-driving car, nobody's going to sit behind the wheel and say, that is a stop sign, right? You have a classifier that is going to make that decision for you. And that classifier is going to take a look at that and say, that's a spoon. So I'm going to pass this intersection and run into another car.
But what if there is a human being sitting? You would recognize as a stop sign, right?
True, but the whole idea behind having self-driving cars is that you wouldn't have a driver.
No, but my question
If
is,
you
like,
have
if
somebody
human being
then-
can recognize it's a stop sign, why can't the network?
We're not that good yet because of this. This whole area of research is to make that happen, is to bring human in the loop so that we could learn in a way that there is no need for that human being to come and say, that is not a spoon, that is a stop sign. So through learning learning from these adversarially generated examples and understanding that space, we would know how to build better classifiers.
You had a picture there with a bunch of what looked like people, and you said they weren't people though, right?
These are generated images.
But if you show me that picture, I'd say that's a person. Like, you're telling me it's not. So now this is
That's
where
the whole
this-
point, yeah.
Exactly.
As a generator, I could show you that picture and say, hey, what do you think about this, right? But you're right, in a lot of use cases, it's not that simple.
Yeah.
So human brains are neural networks. So has anyone tried to create adversarial attacks on humans so that when you're driving down the road, you're going to look at a stop sign and be like, oh, what's that giant spoon doing there?
There is active research in a few universities in the US that is actually doing the same thing. And if anybody knows Tom Mitchell, he has one of the most famous books on machine learning. In Carnegie Mellon, he started doing something like that, I think a few years, like 4 or 5 years ago as well.
That's probably even more dangerous than the autonomous car.
Yeah, because then you don't really have gold standard labels. Because even if the human being can be fooled, if the human brain can be fooled, then there's nothing to go
Actually,
against.
there are certain images, the puzzles, that whether it's a 2% or how many animals you can see. So those are kind of pictures actually puzzling your human eyes.
Yeah.
Blue and gold dress.
Hmm?
The blue and gold dress.
There we go.
Yeah.
Magicians.
One comment, I guess, with the first question, the latent spaces in the literature that I've read are often much lower dimensional than the outer space. So say, for example, your latent space is 1,000 dimensions, your actual space is 1,000,000 dimensions, so there's several orders of magnitude difference. And you could, so the latent space being any arbitrary representation you like. For the sake of argument, say it's like a linguistic sentence that describes the picture. So it might be something like, fuzzy black and white bear sitting on green vegetation, or something like that. And in fact, an artist or even somebody not an artist could draw a picture of that and perhaps present that as kind of a generator to this discriminator and say, does this look like a panda, is kind of what it's trying to simulate. So that's what you could see going on here.
I think so definitely I agree with you. I think that is still a representation space, right? So it doesn't matter, for example, in the case of text that you mentioned, it doesn't matter if you have a 10 million dimension space for a 300 dimension space. You're still representing your sentences or words into that dimensionality. So how much time do I have here?
It's 8:33 now, so.
Okay, so let me know whenever.
Yeah.
When you guys want to leave, just wave in.
I don't even know what's on.
Okay, so just back to
Welcome to the room.
what happened. I need to be part of that conversation because you guys are laughing. I think that's more fun.
It's a good thing. It's a good thing.
Okay, so
Laughing with you.
I want to laugh too. That's what I'm saying. So the generativeness. Let's just wrap that up and then go on to something that is more interesting to me, at least. You will see it's not that interesting to you. So the goal here is that you want to generate new samples of data from a distribution, right? The distinction between your D and G, which are technically two mathematical functions, is that G is trying to learn the joint distribution of that space, so P of X and Y, your input and your labels, but your D is trying to learn the conditional distribution, or the probability of your Y given your X. That's the major definition between those two. So once you have your D trained properly, while you are improving your G and vice versa, then you can sample from this space that has been learned by your G function, and those are going to be your generated samples. So basically what is happening here is that you are trying to get those probabilities from that space that you are trying to learn, or the distribution that you are trying to learn. That's the whole concept of generativeness that is happening here in probability language. So back to your feedback. Anybody here who's heard about autoencoders would say, well, this is the same thing. You want to add something? No, go ahead.
No. I have nothing to say.
Cool. So, say very similar if you know what autoencoders are, but not exactly the same thing. Over there as well, this is basically a very simplified autoencoder. What you have is that you have your input, so let's say pixels drawn as a vector, and then you have two back-to-back networks that are kind of attached to one another. So you have in one part of your network, which is your encoder, you're trying to go from a 10 million dimensional space all the way to some latent space that is encoding your input space. And then your decoder is going to do the reverse job. From this encoded version or encoded representation inside that latent space, you are trying to rebuild the actual data point that you started with. So for those of you who were at KIC last month, Maria was talking about the fact that systems like autoencoders are being used in translating, and that's exactly the same thing. So you start with some English language sentence, and you get some representation in the latent space that then you could use to translate into French. So that would be your input all the way to your output, and the latent space is where you are encoding, you're packing all the information that is included in that sentence. So you sure you don't want to add anything to that?
Oh, no, I got a bit excited.
Me too. So this is what it is. That's basically your original image. You pass it into encoder, you get some compressed representation of that, and then your decoder is trying to rebuild that. So you can see that the tail of this number 2 here is slightly different, but it still looks like a 2. That is where the encoder and decoder are not completely supporting, the translation from input to output, but you could still generate something that looks very similar to what you started with. So in that sense, it is trying to kind of generate something, but the fact that the encoder and decoder have to work together in this way, back to back, as opposed to try to compete against one another, is the difference between autoencoders in general and generative adversarial networks. Now, let's get to how it's different from reinforcement learning. There is a game theoretic aspect when it comes to generative adversarial networks, and this is where it gets interesting to me. First of all, for those of you that might make that mistake, game theory is not game plus theory. Don't make that mistake. I made that mistake once, and that cost me a job. I didn't know what I was talking about. But we only care about one specific concept in game theory. So I'm not going to go into the economics or social science aspect of game theory. All I care about is this concept of the probably most famous concept of game theory, which is the Nash equilibrium. And the gentleman on that side is John Forbes Nash. Some of you might know him.
Beautiful mind.
Because of Beautiful Mind, thank you. Obviously because of Nash equilibrium, because he's the person who proved that this exists, and probably some people here might also know him because of his PhD dissertation, which was the proof of existence of this, which is just 28 pages. So you could try to read it, but I bet that it will take years to understand. So he's famous for different reasons, but most important thing is Nash equilibrium. So I'm going to read what Nash equilibrium means in words, and then I will try and make sense of that. So Nash equilibrium is a proposed solution to a non-cooperative game. So that's one important aspect of it. You are playing a game which is non-cooperative, or you're competing against one another, which involves two or more players, in which each player is assumed to know the equilibrium strategies of the other player. Not going to go into details of that. And no player has anything to gain by changing only their strategy. So, before understanding what this whole thing is all about, I just wanted to make 2, maybe 3 points. One is that this game, this non-cooperative game, needs to be a minimax game, or in other words, a zero-sum game, which basically means if I'm losing something and in a 2-player game, and you are winning something, the sum of those is supposed to be 0. So if I have to lose 100 bucks, for example, if I'm gambling, then where I'm gambling is going to gain 100 bucks. That's a zero-sum game. That's the basic definition of it. But we also use the term minimax for that. And the second important point in this is that it is an equilibrium. This is not the optimal strategy to win the game. It's just a state in this game where, based on what you can see up there, as a player, if I only change my strategy, I'm not going to win more. That's it. So I have to make you change your strategy before I change my strategy so that I can win something extra. If you stick to what your decision has been so far, and I change my decision, then I will lose. That state is the state of pure Nash equilibrium. So if this is how you feel right now, yes, you should. But let's see what it means in numbers. So you have players A and B, and then each player has 2 options, 1 or 2. So that is why each player is assumed to know the equilibrium strategies of the other players. So as player A, I would always win this number that is first in each cell, and as player B, I would win the second. So if I'm playing against you, then I would win the first number. Let's say you would win the second number. So we're playing in that sense. If I choose option 1, so this row, sorry, if player A chooses option 1, which is this row, as player B, if you go from option 1 to option 2, you would go from +1 to -1. So there's no incentive for you to change your strategy. If as player A, I am choosing option 2, same thing. You would go from +1 to 0. So you don't have any reason to choose, to move from option 1 to option 2. So that is why player B always sticks with option 1. Same story for player A. If I know that player B is going to choose option 1, me going from option 1 to option 2 is going to result in me losing. Same thing. If I know that you're using option 2, I'm going to lose. So I'm going to stick with option 1. That is why option 1 and option 1 are the Nash equilibrium of this game. Now, it doesn't always have to be the same options. This case, if I know that this is what you're choosing, I go from 2 to 1, I'm going to lose. If this is what you're choosing, I go from option 2 to option 1, I'm going to lose. Same case for player 2. So option 1 and option 2, or option 2 and option 1 for players A and B are going to be the Nash equilibrium. Not all games have this state, but John Nash proved that if you have this type of game, you always have a pure Nash equilibrium. Some games also have some partial Nash equilibrium. And it's also not only for 2 options. You could have multiple options, you could have multiple players, And for each pair of players, you would have one of these matrices based on the options that you have, and some of those games are probably going to have a Nash equilibrium. Why do I care about this? We thought that we're done with numbers, we're not yet. A game, as we decided, is Minimax if and only if you have two players, and in all the states, the reward of each player, for example, player 1, is the negative of the reward of player 2. So in that sense, you have a function, x and y, and then the min of the max of function 1 for these two states that are decided by these two players equals to the max of min of function x and y. That is the mathematical definition of a Minimax game. The Minimax theorem states that any point satisfying this is a pure Nash equilibrium. And side note, as I mentioned, this is not the best way to win this game. It's only it's not optimal. It's just an equilibrium. So if the opponent knows your strategy of choosing your options, it's always better to use a distribution of actions as opposed to just sticking with option A and always playing that. Now, why do we care about deep learning then? Or how does this connect to deep learning? If you have this, so I was lazy, I didn't want to type, so this is the same thing, F that you saw on the previous slide. If you assume that your players A and B, your players D and G, in the sense of discriminator and generator, have access to the states A and B and can define these variables X and Y, the Nash equilibrium for this happens when X equals Y equals 0. And if you want to solve that, then you end up using gradient descent or a set. So that looks like deep learning for me. That's why we need deep learning models. Or any model that's using a neuron-based architecture, so to speak. And you could also see that, so we'll get back to that. Time for real math now. How is this whole thing connected to Nash equilibrium? This is how it is. So in theory, you want to learn the distribution of your data. And if you want to do that, then you want to devise a two-player game between your discriminator and your generator, your two agents. Again, in theory, you could assume that you have infinite capacity. So what G can do is it can declare a distribution in a data space, right? So this is how an integral is different than a summation, right? An integral, you assume that you have infinite capacity over the space of your axes. So G declares a distribution in the data space over all the potential samples, and D declares a value between 0 and 1, similar to a probability, for each and every point in that data space. And when it comes to the payoff time, the reward, D wants to assign low values for points that are likely coming from the distribution of G, and high points or high probability to those points that are coming from the actual real data distribution. That's how D is going to get payoff. So the payoff functions are going to be the V for any x that belongs to the actual data is going to be related to the log of the dx, the function dx. And for G, the points that belong to G is going to be relative to the log of 1 minus dx. And then if you sum them up and try to use gradient descent, the sum of that is going to result into a Minimax game. Now, in reality, we can't really do that. We cannot go and say, hey, I'm going to declare a distribution over any and all data points that could potentially exist. So you have to enforce some finite capacity. So instead of G giving you a distribution in the data space, G would broadcast M fake data points, right? And then D, same thing. It has M real data points and M fake data points, and it's trying to declare some value for each and every of these 2 times M data points. One thing that is important here in order to solve this problem is that both of these strategies should be differentiable so that we could use neural networks. So again, D wants to assign low values or low probabilities for things that are coming from G, and high probabilities or values for things that are coming from your real data space. And in the payoff then, we can only use approximation of the expected value of any point belonging to those data spaces because you do not have access to the full distribution of the data. So what you could do to solve that approximation is using gradient descent or ascent is to update D by ascending its stochastic gradient and for G to update by descending its stochastic gradient. So that is how they're working against one another. That's how game theory comes into play because you're having G and D playing against one another. And that's how deep learning is involved in this whole thing because you're using differentiable functions to try to estimate something that you do not have access to the full distribution or the full spacing.
And the second last point, D wants to assign low values for points likely to be from G.
Yes.
And high values for points likely to be from a real distribution.
True.
How will you know that it is coming from a real distribution? I mean, how will you know?
Your teacher. This guy. When this guy provides some feedback, you would know if the thing that you have generated gets high probabilities from your D or low probabilities. If you are getting low probabilities, it means you cannot fool your D. So you have to change your way of sampling noise. And D would know that it has made mistakes, so it's trying to improve itself. So the teacher is the most important component in this whole scenario. The teacher is providing feedback.
So this is maybe really silly comparison, but it's like the teacher kind of like the referee in the game.
It is, yeah.
This is a goal, this isn't a goal.
True.
And then just to deal with the whole concept as well, I'm starting with, are we basically trying to break the discriminator and say, okay, it can't hold up, it's failing. We have to improve the model, or is it actually learning the process?
So the goal of discriminator is to be a replica of your teacher over time. So best case scenario, let's say you train this for 1,000 iterations over some GPU, and you would have a discriminator that could, with 99.99% accuracy, give you the same result as your teacher, right? So through moving into that, through ascending that gradient, your D is going to get better and better and better over time, but it is also working as an entity that is providing feedback secretly to your G. So your G is going to generate better samples. So by the end of the day, you are going to generate fake samples that are 99.99% going to bypass your actual referee or teacher because your D is trying to replicate that behavior.
Okay.
We good? Questions?
Okay. Are we assuming that the teacher does have perfect information?
In most of the cases, yes, that's the assumption. Or the realistic assumption is that this is the best we could ever get in real world. So yes, we assume that it's 100% accurate.
The theory, the last slide that you presented, I think has been developed after the adversarial AI practice was done, yeah?
So they started in late 2013, beginning of 2014. It was not as complex. They knew that they were moving towards making it a game theoretic domain, but I cannot say for a fact that this existed in the actual paper, because last time I read that was a long time ago. So I don't know the answer to that question, to be honest.
Can the generator really reach 99% success?
Can you speak a bit higher?
The generator.
Yes.
Can it really reach 99% success rate?
Oh, that was just an example that I said. And then the generator doesn't reach 99%. The discriminator is. The generator is just outputting some samples, some fake samples. The discriminator is looking at those and saying, yep, this is, I can't say for a fact that this is a Panda or a given, based on all the training that I've got so far.
My problem is maybe it's saturated at 50%. The optimal equilibrium would be somewhere around.
So I think what you're talking about is the level of uncertainty, right?
I'm talking about, say you have a perfect generator discriminator system.
Okay.
Would the success rate of generator ever go beyond 50%? Wouldn't the ideal value be?
Yes, it would. It could technically, in theory, become 100%. So any sample, any fake sample that the generator is building could bypass not only your discriminator's decision-making boundary, but also your real-life teacher or referee.
But that won't be an equilibrium point, right?
It won't be, what?
That won't be an equilibrium of flow.
No. So in order to get a generator that can create real-looking fake samples, you have to move towards a pure Nash equilibrium. As soon as you hit that point, you know where you're going. So you could go into an optimal strategy afterwards. Because your G and D are working against one another, but also together against another entity. So at some point, because you can bypass your D, and your D is a replica of your real-world teacher, then you don't really need your teacher anymore. You could just start asking your D, and then getting feedback, and improving yourself. So that is how they got to those images. Because at some point, even the human eye cannot distinguish between what is real and what is fake. So this whole thing is until you get to that point. Until you get to the point that you need 3 components. As soon as you need only 2 components, then you go past your Nash equilibrium point.
Awesome. Okay. So you're saying, the point is to use like the classifier at the end, but so since you're training both of these, right, are you not also optimizing your generator to generate, right? So when I'm looking at this and I see like, this person, this is not a real person, right? That looks like something coming out of like a generator, right? So in your experience, is it difficult to sort of uncouple the 2 models and then just use the generator? Like say you wanted to generate like text, or you wanted to generate some essays or something.
Nope. So as soon as you hit that point, then it's no longer that hard. Okay. The whole problem with this is to make sure that you are on the path to getting that pure Nash equilibrium of D and G. As soon as you hit that point, or as soon as your G is quality enough, then you don't need that component anymore. Then you could start building whatever you want with your G, because you know that your G is very good at replicating what is in reality. And there's no game after that. It's just G is always going to win.
Again, it might be a very basic question, but the question is like, what if the G is generating, G knows that it's less reliable because of the teacher. Teacher is putting like the reliability tag on G less. So to fool it, it now not generating fake images. It is giving a lot of real images, and it is now becoming lower rank. The real images, stop sign or pandas are becoming a lower reliable.
No, I have
Ocean's 11 kind
seen
of.
Yes, I have seen of those cases where G is actually trying to fool D and the teacher by feeding in real images, but that is based on the assumption that your G has access to those real images. So if you assume that your G is limited to those types of the real good images, so you could have real bad images, for example, real fake images, or real images, right? And then generated fake images. If you can have access to the real fake images, or real things that you know that somebody else has put up, let's say with Photoshop or another network, then yes. Sorry, if you have abnormal. But if you only have access to the real fake images as opposed to what I have generated, then I can't do that. So there are 3 different types of basically things in the data set.
So when we look at the images, it's understandable. But when we go to intrusion detection system, how do we relate it? Like, how do I get a generator what is the generator trying to do? Like, is it trying to generate malicious things or?
Yes, so what it does is, it really connects to this point. And let me just bypass the math and go into some of these examples, and that is where I could talk about the intrusion detection system. So the IDS or IPS intrusion prevention system is basically this. It sits right there and it tries to stop the packets from going into your computers, like malicious packages, right? Don't care about all of these, we can talk about them later, but this is what's happening over there. What happens is that you have some normal traffic that is good, right? Real images. And then you also have some real fake images. And you use them plus some, hello. You use them plus some noise to feed into your generator, and then you generate some adversarial malicious traffic, which is what you're talking about, right? Which connects to your point. And then you try to train your discriminator by asking a question from an IDS system, which is a teacher, that you do not have access to how it works. And then through calculating the loss function, you keep updating your discriminator, right? How it looks like, it's just the latent space that we talked about. You take a bunch of features that you care about in this domain, and you translate them, you pre-process them into some space that is just purely numerical, right? Now, when it comes to the generator, it's doing the same thing. It generates something, and then based on this malicious traffic and the noise, it passes into the discriminator, and then the discriminator starts by randomly guessing whether it is malicious or not. And over time, it goes away from randomly guessing to actually knowing which packet or which representation of a packet is malicious and which ones are not. And because over time your discriminator is getting better, then your generator has to get better in order to fool it. Now, if you want to know what these look like, then you have to take the good examples that are fooling your discriminator after training, after reaching to that Nash Equilibrium point, and take them through the reverse pre-processing that you're doing here. So that you could take a look at that vector of, let's say, 1,000 different columns, and bring them back to 14 columns that you care about. You understand what is happening. And then put them in front of somebody like us, who is a subject matter expert in this domain, and say, do you think this packet is malicious or normal traffic? Or pass it to an intrusion detection system, which is your teacher or referee, or would you block it? And then through doing that over and over and over in time, through whatever number of iterations, you would end up having adversarially generated malicious traffic that could bypass any IDS system. I don't think I have enough time.
It's 9, so.
Yeah. So this was the last example. You start from there, add some noise, and over time you get better and better all the way so that you can build that. I know.
Right on.
No.
That's great.
Awesome.
It seems like from Picasso to Vinci.
Yes, sir.
Go up to the slide that open all the question, please.
Which one?
The slide for the graph that show the classifier and the generator.
The one for the IDS or the previous one?
The previous one.
This one.
This discriminative, only one model to classify between the images. So use one model, one model.
Well, what I have seen is just one neural network.
So one model.
You could have more.
So one component is enough, but the main one and the other one.
Agreed. Yes. So if you have a meta classifier over there, you make this guy's job very hard. But if you can't bypass the meta classifier, then you can bypass anything.
So one of the questions. So what will happen if the classifier and the generator end up like classifying between rooms images like pink for the fish and black or white for the panda at the end of the images, and you don't know how to select the features, so how to
I have to think about that. Let's talk in person. I think Mary wants to kick us out. let's talk in person about
Yeah,
that.
you can definitely. Yeah, you can share your email address, and Armand is like really happy.
No, right after this. And I will share the slides with you, by the way.
Cool. Thank you.
Anybody wants a picture of that? It's okay.
Yeah. And if you all can help out a little bit with rearranging the tables back, then we can.